The chain rule is going to combine all of the derivative rules that you've memorized so far with your advanced algebraic knowledge of function composition. Last year in pre-calculus, in an entire section, we looked at a complex function and then ripping it apart of finding what function had been put inside and what function was on the outside so that we could rewrite it looking at two separate functions. That entire section was getting you ready to be able to look at functions and apply the chain rule. Don't worry if you feel that the chain rule theorem looks a little complicated. The chain rule actually makes deriving a lot of fun. It's one of my favorite sections, and I'm going to be breaking it down for you nice and simple and in color. So I hope you enjoy it. We know how to differentiate all kinds of functions, trig, polynomials, products, quotients, but we're going to be faced with functions that are composed one inside of the other, and that causes us a problem because our derivative rules can't handle composite functions. We need to look at the composed functions in layers so that we can clearly identify the function that's on the outside and the function that's on the inside. We're going to derive the outside function first, leaving the inside written exactly like it was in the original problem. Then we will multiply by the derivative of the inside function. So our function h of x is equal to sine, which is on the outside, of x squared minus 4, which is the inside function. I like to write the layers in color so that I can see how many things I need to derive. So I have h of x is equal to sine, this is my outside function, and the x squared minus 4, which is my inside function. So deriving the outside, don't forget to always put your label first so that anyone reading your work can tell what you were starting to do. I derived the sine, its cosine. I leave the inside alone. Don't alter it in any way. But then, because it's different than 1x to the first power, we multiply by the derivative of what was inside. So the derivative of x squared minus 4 becomes 2x. My final answer, I'm just going to clean it up and bring that 2x in front so it doesn't accidentally get sucked inside the cosine because we're not allowed to alter our angles. So I put the 2x multiplying in front times the cosine of x squared minus 4. And this is my final answer. I chose this example for two reasons. First, because you already know how to derive it using your quotient rule. And second, because I wanted you to see how the chain rule makes your work a little bit easier. So using our quotient rule first, g prime, we derive the numerator, it's a 0, we keep the denominator. We subtract, we keep the numerator, we derive the denominator. And we divide by the denominator squared. Cleaning it up, 0 times anything is 0, and we'll distribute our negative 1. So we get g prime is negative 3x squared minus 2 all over x cubed plus 2x plus 9 squared. Now, let's rewrite it so that we can apply our chain rule. So as long as I bring the denominator up as a unit and not as individual pieces, I can put everything to the negative 1 power. And what's inside is just my polynomial. So using my power rule, I'm going to derive by the negative 1 dropping in front and the power subtracts 1. I leave the inside exactly how it was, and I multiply by its derivative. Quick and easy. Now, rewrite it. Clean it up. Anything to a negative power drops on the bottom. And my negative 1 is going to distribute into the polynomial left on the top. So I get negative 3x squared minus 2 on the top, all over x cubed plus 2x plus 9 quantity squared. And my derivative is exactly like the derivative I got by using the quotient rule. So quotient rule, chain rule, which is better? You decide. Okay, so let's do another example using the power rule. So my outside of my function is the power. My inside function is the polynomial. So when I derive, the outside, the 8 drops, 8 minus 1, 7. The outside is derived, and I leave the inside alone, leaving it purely how it was written in the original problem. Then I multiply by its derivative. We don't want to multiply this out. Remember, at some point we are going to start setting these equal to 0 or to other constants and then factoring and solving. And so at this point, if I was going to set this equal to 0, I wouldn't want to have to factor it again. I like it just how it's written. So this is my final answer. In this example, we have another quotient, but we're going to leave it written as a quotient because if you can tell, not only do we have a quotient, we have a power wrapped around it. So my outside function is that power. My inside function is the quotient. So just deriving the outside first, drop the power, subtract 1 from your exponent, leave the inside alone. Now, deriving by the inside, I have the numerator is a 1, and keep the denominator, subtract, keep the numerator x plus 1, the derivative of the denominator is a 1, and divide by the denominator squared. Now remember, at some point we're going to want to set this equal to 0. So I'm going to show you how I'm going to look at it to clean it up. So I keep the 4. The x plus 1 and the x minus 1 both individually are cubed. So I want to look at them as a numerator and a denominator. And this is why. Because my denominator on the other side matches. And I'm going to be able to combine these two. Simplifying the top, I get x minus 1 distributing that negative minus x minus 1. The x's are going to cancel, and I get negative 2 on the top. So simplifying just a little bit further, 4 times negative 2, negative 8. I have x plus 1 cubed in my numerator, and x minus 1 to the 5th power in my denominator. The chain rule helps us out so much because this would have been horrible to have had to multiply and then derive. In this example, can you tell how many layers there are? I'll write it in color so you can see all of them. The first layer is that power. The second layer is the cosine function. The third layer is the angle to theta. We have to derive each layer separately. So y prime, drop the power, subtract 1 from the exponent, and 4 minus 1 is 3. Leave everything else alone. So the cosine stays, the 2 theta stays, and we're ready to look at that inner layer. So black layer done, ready for the red layer. Cosine derives to negative sign. So the first thing I take care of is my negative by putting it out front where it will not get lost or be mistaken as a subtraction. And then I say, here's my sine function. Don't touch the angle. Keeping my angle pure, and then multiplying by its derivative. So we have 2 multiplying to the 4. And on the outside, as I simplify this and clean it up, I get negative 8 cosine 2 theta quantity cubed sine 2 theta. If I were going to set this equal to 0, it's factored. I could actually solve for it. However, there is a trig identity hidden in this answer. So if you can find it and put it in your comments, it just might be worth extra credit. Only 2 questions for the Google Doc tonight. Do your best on them, and don't worry if you struggle a little bit. We're going to be doing a lot of examples in class in addition to these 2, and it's going to take us a couple of days so that you guys have a lot of practice and get really proficient at it. Your homework, also, I know it looks like a lot, but again, you're going to have a couple of days to work on it, so no worries.